Alright guys, this is problem 19.19. The problem says two cars collide head-on while each is traveling at 80 kilometers an hour. Suppose all the kinetic energy is transformed into the thermal energy of the wrecks. What is the temperature increase of each car? You can assume that each car's specific heat is that of iron. Alright, so as usual, we're going to write down what we want first in simpler terms. So we basically want the rise in temperature for each car, as the problem says. We're going to use the variable delta T for that because it's the change in temperature. So basically we want the change in temperature for each car. Specifically each car on its own, not both of the cars combined. Alright, so I do this picture here to visualize. Move the light a bit. Okay, so as you can see, we have two cars going at each other at the same speed, 80 kilometers an hour. And then as far as equations we know to be true, we know heat absorbed is equal to mass times a constant times change in temperature, or Q equals MCAT. We know, so this is an energy problem, and the problem specifically mentions kinetic energy. And if it didn't mention it, we know that since these two cars are moving objects, we know that the energy, specific type of energy involved would be kinetic energy, which is equal to 1/2 mv squared, as we see here. And then for both of those two equations I just mentioned, in terms of this specific problem, since there's two cars, we're going to add a second term to each equation. So whereas Q is equal to MCAT, Q total in the context of this problem is equal to MCAT of the first car plus MCAT of the second car. And likewise for energy, we know that the total kinetic energy is equal to the kinetic energy of the first car plus the kinetic energy of the second car. As far as tricky parts of the problem, this is probably the worst part of it. I first did the problem without adding in the second term, and then I realized I was off by a factor of 2, because you have to add in the second car, otherwise you will get the change in temperature for the whole system rather than for each car individually. All right, and the last key point we need to know is the law of conservation of energy. We know that the energy at the start of the system, or at the start of the problem, has to be equal to the energy outputted at the end of the problem. Yeah, so let's get started with solving the problem. So again, we're going to start with the law of conservation of energy, which says that energy in has to equal energy out. And then going from there, sorry, I'm trying to fix the lighting here. All right, so we know energy in, we just have to figure out what energy in is and what energy out is, so we can break this down a bit. All right, so the problem states that kinetic energy is turned into thermal energy. So we know that at the beginning the cars are moving toward each other, so they have kinetic energy, and then once they crash, all of that energy is released in the form of thermal energy. So in other words, we can say that E in, or energy in, is equal to the kinetic energy total, and we know that energy out is equal to the total heat absorbed. All right, so again, we're just going to substitute based on what we just talked about. So now we have Ke tot is equal to Q tot. And then, as we mentioned earlier, we can take the equations we derived that are specific to this problem with one term for each car and substitute for Ke tot and Q tot. And we get this. And then we can just rearrange this a bit. Or not rearrange, simplify rather. So we add these two terms together on each side. And then we get this, mv squared is equal to 2 MCAT. And then just rearranging this, again, we're looking for the change in temperature of the system, or each car in the system rather, sorry. So we're going to isolate for the change in temperature, which will give us v squared over 2c. So this is our answer. We know it's an answer because it has what we want, delta t, written in terms of only things that are known quantities. So we know velocity, it's given in the problem as 80 kilometers an hour. And we know c. The problem mentions that we can assume the car's specific heat is that of iron. So the c for iron is 449 joules per mole Kelvin. So yeah, so this is the answer in abstract form, and then going in and plugging in all the known values. The top just looks so complicated because there's a unit conversion from kilometers an hour into the SI units, and then we put that over 2 times the constant for iron, and that should get you about 0.549 degrees Celsius. All right, that's about it. We mentioned tricky parts of the problem. As far as context of the problem is really just trying to get you to be able to manipulate this equation, Q equals MCAT. And I think the biggest conceptual takeaway I got from this is that seeing this Q symbol as a type of energy rather than just its own separate thing. So this problem kind of teaches you how to relate different types of energy together and how to treat this thermal energy as just another form of energy, like you would compare potential energy to kinetic energy. So yeah, thanks for watching, guys. Bye.